Pueblos. Okay. Showing us the robot. So this is Kirk Miller, who's one of the mentors of the team, and the team is here. And take it away.
All right, thanks, Yvonne. As she mentioned, my name's Kirk Miller. I'm one of the mentors for the Octobots Robotics team at Dos Pueblos. We have our two lead mentors here, Michael Ramsey and Michael Cameron, both in the room. So we have four of our team members here. So I'm gonna let them introduce themselves and then give you all an introduction to the robotics program, the program that we take part in, and the program at Dos Pueblos, and explain to you about the robot that we built in the last year and what we're looking forward to in the coming year. So
I'm Alex. I'm the software lead for our team. So I handle delegating the software tasks and making sure the software for the robot is good for competitions.
Hello, I'm the strategy lead. I'm Sierra Kendick. I'm also part of the DPA, which we might mention a little later. But yeah, I handle the strategies, how we should compete in competitions, and yeah, and who should we team up with?
I'm Richard Steele. I'm an auditor. Okay. I am the project manager. I keep track of what everybody is doing and making sure everybody is on track and making sure everything gets done before competition.
I'm Daniel Herring. I am, this is my second year on the team. I'm business co-lead and also on the CAD team. And I'm hoping to be one of the drivers for next year. I will be driving with Desi Tams, at least during a couple of matches. We'll see. Yeah.
all right. Thanks, everybody. Okay, so we've got some slides to kind of help set the scene here. And of course, we brought the robot. So first, let's see how I can change here. Next slide. Okay, so first of all, the competitions that we compete in is part of what's called the FIRST Robotics program. FIRST Robotics has 3 levels. There's the FIRST Lego League, which is Legos on a tabletop for elementary and junior high school kids. There's what's called the FIRST Tech Challenge, which is robots that are about 18 inches square. They play on a field that's about 10 feet by 10 feet. This is junior high school and high school teams. And then the one that this team competes in is called the FIRST Robotics Competition, or FRC. The robots are about 3 feet square. They weigh 125 pounds. They go 25 miles an hour. The field is about 54 feet long. This is a program for high schools. So you'll hear more about the games as we go on, but it kind of gives you an idea for the size and scope of the robots that we are driving. This whole organization was founded by Dr. Woody Flowers, who picture you see in the upper right there. And he had the vision for this competition founded on this idea that he had called gracious professionalism. So this is what we all work to. So we reinforce it at all of the events, and we practice it at our team practices, where we are always looking to help each other out, or the competitions are friendly. We don't get too excited if we win or if we lose. And we then related to that is this notion at the bottom here, you can see a cooperation, where we're competing, but we're also cooperating. So the games typically have some element to them where the competing robot alliances, if they work together, then everybody gets extra points. So you get the idea that this is a character building in addition to building STEM skills for the students and the mentors and everyone involved. A lot of you may have come across Dos Pueblos engineering robotics teams over the years. So from 2006 to 2015, the Dos Pueblos Engineering Academy had a team that was team number 1717, the Penguineers. You can see a photo of them here in their iconic black jumpsuits that you may have seen. They actually drove their robot around the Science and Engineering Council meeting back in 2011. So that was exciting. That team, they changed their focus from competitive robotics to a different focus, and so that team shut down. And then off campus, there was a team that formed called 5818 called Riviera Robotics. A team picture here on the bottom right, and that team went from 2016 to 2022, and it's sort of in hibernation right now. So with no team to join, a group of mentors and students formed the Octobots, which is team number 9084. So that's what you're seeing today. So if you can see the robot in front here, you can see the 9084 numbers on the bumpers. So that's the current team. It's a Dos Pueblos affiliated club. And so the students are all Dos Pueblos. So we have some folks like Sierra from the engineering academy. We have a lot of students that are not in the engineering academy. And then the events are all school, field trip type events. And that's how the current team is operated. So, do you want to talk about the mentors here? So I don't have to.
Yeah, I can talk about mentors. So we have 4 main mentors, 3 of which are here. We have Michael Ramsey over there, Michael Cameron in the back, and Kirk Miller over here. Yeah, and then we have John Reedman, who is not here, but yeah, he's also a mentor.
All right. So this team uses a lot of tech. So I don't know, Alex, if you want to explain a little bit about the stuff on the software there is right next to you.
Yeah, so we program in Java, and we work off a lot of libraries that FIRST provides to interface with the motors. We have this processor called a Robot Rio that is quite slow for running stuff, but we make do. We communicate with the motors over a CAN bus, and we use gate controllers for our motor control to, for example, like we have an arm on the bottom we use gate control for. We interface with gyros to make sure to allow the driver to better control the robot and drive relative to the field. We also have some vision capabilities on our bar that are powered by photon vision. We detect tags that you can see here in the bottom corner that are placed around the field. Those give us the robot's position. And then from there, we can do some calculations to calculate the optimal angle to shoot at to make it into whatever target we need to make it into.
And you do that by using Raspberry Pis.
Yes, we have 2 orange Pis on the bot that we use as co-processors to process the vision. And then we do version control of all of our code through GitHub.
Does one of the CAD folks want to talk about the?
Alex, how many people work on software?
Probably around 15 or so people. It varies, but overall around 15 members, probably per meeting, around like 7 to 10 members. But 15, yeah.
How many lines of code? I don't know the answer, actually.
I can't actually, I haven't checked, but it's just a lot of code.
All right, someone want to talk about the CAD tools and?
Okay, I guess I could talk about SolidWorks. So we use a 3D modeling program called SolidWorks. A lot of people probably know about it. We use it to CAD all the 3D designs for the robot and to make sure we're using the right measurement, make sure it works out before actually building it together because we want to not waste material. We also use a CNC machine, which is basically a computer operated mill. And then we also have 3D printers where if we make a part on SolidWorks, for example, make a 3D design part, SolidWorks, we then can 3D print it on 3D printer. And that's about all I know with
Yeah.
SolidWorks.
I'm just gonna pull this out real quick. So this past season, our robot had to climb up chains. So we just Luis, who's one of our now graduated, but he was one of the seniors last year. Him and his team designed this in SolidWorks and then cut it on this. And they were
CNC.
progressively, on CNC, or progressively iterating on it throughout the entire season.
to then develop.
Yeah, you know, you have to do that. The motors will.
Yeah,
it's gone. Motors are too strong. Well, it's hard if you can actually pull it up. I can show you the climate. So you'll just have to wait until we're actually driving it. But yeah.
Right, yeah, and as Alex mentioned, the processor for that's sort of the brains of the robot is this gray box at the top of the slide. It's a National Instruments Rio controller, so it runs embedded real-time Linux on a Zinc processor, which has FPGA fabric that handles all the I/O and all the real-time stuff, including CAN bus.
And we use
Yep.
Canvas, which is part of the wiring.
Yeah.
And we also do all the circuitry on the robot, which takes time because it's a lot of organizing wires, connecting stuff together, making sure we're soldering, connecting them all right. Because if they're not connected right or they break, the robot will not work. So it's also a very important aspect of the robot.
Okay. The team is funded through sponsorship. So we have a bunch of companies listed, and you can see we've got a sponsor panel on the robot that you're probably looking at in the camera. And then here's a photo of it.
Oh,
We also
Job.
put sponsor names on the back of the t-shirts, and you can see this is our pit operation here at one of the competitions. We've got the sponsor names on the banners. So we've got different levels that companies can sponsor the team, and you get different levels of of goodies from that. So that's a great opportunity for these students to go and engage with the community and go work to get those sponsorships in. And
I would also like to add that it helps us gain more leadership skills and communication. And so it definitely helps us improve talking with others. Because obviously, if you work at a company, you understand how to work with other companies and work together as a team. So it's very helpful to help. It's very helpful to communicate with other groups, organizations.
Team's a 501c3 nonprofit, and we go on trips. We have to buy obviously hardware. We build a new robot every year. That's several $1,000s worth of parts, and then the registration for the different events costs money. So this is where most of it comes from. Okay, so what's a year in FIRST Robotics look like? Does someone want to talk to this, or you want me to talk it through?
So around the start of January, past couple of years, it's been like the 6th, I think, we get a new game that is released, which is basically a series of tasks that are on a standardized field. So the field dimension is always the same, but the tasks you have to do are different. So for instance, last year we had some cones and then some like inflatable cubes that we had to take from one side of the field to the other and place in specific locations. And the speed at which you could do that determined basically how many points you could get. This year, it's a similar thing, except we have these new game pieces called notes, which some of you may have seen before, but if not, here it is. It's a foam ring. And these we collect on one side of the field, we take them to the other side of the field, and we put them into various field elements. So one of those is we shoot it into a high goal, and we also shoot it down into a lower goal. And then at the end, we use the climb towers that were mentioned earlier to climb up, and then again shoot the note down into a little contraption that scores it. And the game changes every year, so we have to be very strategic about our robot designs, where we want to put most of the effort in, what motors we want to use, and how we want to accomplish each of the tasks, how we want to prioritize each of them. So,
Yeah, it's important to like strategize what task do we want to be able to do the best. And because whenever we can do the best determines what our position is in the competition. If we want to be more a robot that can move fast, shoot more goals, we're going to be earning a lot more points. If we can do trap, which is what he was explaining earlier, where we flying, that could give us a lot of points near the end. So it really, do you want to be supportive? Do we want to be offensive? Like it's basically, we had to think about it because there's many different ways to go about it.
So we typically compete in 2 to 3 regional competitions each year, and those are what qualify you to go to World Championships. If you win the event in an alliance of 3 teams, if you are one of the top 2 teams in that alliance, you're basically guaranteed to go to champs. Otherwise, it kind of trickles down depending on certain awards. We went to championships our rookie year, which was the year before last, through both the Rookie All-Star and also being a finalist for an event. We also do various off-season projects in the summer for teaching new students how to program, how to CAD, basically how to create the bot from scratch. And we go to a couple off-season competitions. This year we're going to 2. We're going to Chessy Champs, which is coming up at the end of this month in San Jose. And we're also going to Tidal Tumble, which is in Ventura. Chessy Champs is actually not a typical off-season competition. You have to actually apply for it. And it's quite competitive. So you get a lot of good teams who go, basically, for that.
Yeah. Basically around like the top 30 teams. It's like, well, not the top exactly. They are the top, but what Chessy Champs, so Cheesy Poops considered on the top teams, and we also got accepted in, so.
Should I show the video for this? Oh, go ahead.
Yeah, I was just gonna say, like, what happens in January? Like, and make it more remedial, right? We receive a PDF,
Yes.
right, that explains the new game rules every year.
The manual is always so much fun to
And then
read.
how long did we take to build that robot?
Oh, yes, I should have mentioned that. We have around 6 weeks or so until the first competition, I believe. So it's quite the tight timeline. We have to decide how much time we want to divide between actually building the bot and then programming it, because if we do more software, then we can get more advanced software features. But without the hardware to back it up, it's difficult.
Yeah, so just to kind of take a look at the robot that's designed and built 100% by high school students in 6 weeks.
Yes, it is just being 56 years and $1 million probably.
So yeah, as I said, strategy is actually one of the things, like, we need to strategize how to spend our time wisely. And all fit all the construction of the robot into those.
Yes.
Why don't I show the video for the current year's game? So this is what we get on the first week of January, is we get a video that looks like this. Oh, sorry, this is the release of the, sorry.
We also get a
This is
really
the
rough
release,
PDF
this is the
that plays
teaser for the coming game. I
Well,
apologize.
this is the 2025.
We're diving in. The ocean is more than what you can see on the horizon. Beneath the surface lies our planet's most complex ecosystem, full of life and potential for exploration and learning. With this season of FIRST, we're exploring beneath the surface and uncovering the potential in each of us to strengthen our community and innovate for a better world with healthy oceans. Sonars and other marine technology allow us to gain more immersive knowledge of the ocean's greatest wonders, to explore the unknown and apply those learnings to improve life on land and below water. The ocean affects our weather. It provides food. It supports all living beings. And through great challenges, the strength of the ocean's biodiversity sustains it. Your adventure begins here with FIRST Dive, presented by Qualcomm.
So at this point, this is all we know about what we're gonna find in January. So lots of, speculation about will there be water involved?
We're all worried about water
Nobody
games.
really
We don't
knows.
want a water game.
So, yeah, I'm showing it here. So the dive will be the overall theme. The game for FIRST Robotics Competition that we're in, the game will be called Submerged. And then FIRST Tech Challenge will be called Into the Deep.
So yeah.
Rescape is us? Oh, yeah.
So
Sorry.
basically, for like the last 10 years, FIRST has basically put an overarching theme for the season. And so obviously this is an underwater season. And so the mechanics of the game are a mystery and may not really be directly attached, but it's good because it kind of gives visibility to various areas. This last season and this robot we have here, it was a musical theme. The game was called Crescendo. And then they renamed whatever the game piece was. Those are notes. And so
A phone ring is a note.
a phone ring is a note. So
That video has nothing to do with the game. It's just
So
a teaser.
yeah. So what's great about they've got FIRST has a game design committee that puts these games together in great secrecy, but they change the game pieces that you have to handle and score, whether we're shooting them or placing them or whatever the mechanic is. They actually try to make it a fresh challenge every year so that teams that have been around a long time go, oh, that was like that thing we did 10 years ago, and dust off an old design and adjust it. So this is a great program because it's a common problem given to all the teams. And then we end up seeing 3,500 different solutions from all the different high schools.
You wanna find the video showing the kickoff?
For this game,
See a game?
yeah,
We see a match.
oh, here we go. Here's the CAD drawing of the current field, but this is the video of the current game.
Life is a little bad.
It's nice for a lot of stuff.
Welcome to the 2024 FIRST Robotics Competition game, Crescendo, presented by Haas. Two alliances of 3 teams each compete to score or play notes in 3 different field elements. Amplify their speaker, get on stage, harmonize, and take the spotlight before time runs out. Alliances earn additional rewards for meeting specific scoring thresholds and for cooperating with their opponents. Robots start each match inside their alliance's starting zone and may be preloaded with a note. During the first 15 seconds of the match, robots are autonomous and can be programmed to leave their starting zone, play preloaded notes in their speaker or amp, and collect and play additional notes. During the following 2 minutes and 15 seconds, drivers control their robots. Robots collect notes from human players at their source and play them in their amp and speaker. Each time an alliance plays 2 notes in their amp, the human player can hit a button to amplify their speaker for 10 seconds. Notes played in an amplified speaker are worth more points than those scored in an unamplified speaker. A human player may choose to play a note scored in their amp to cooperate with their opponent. If each alliance plays a note by hitting their cooperation button in the first 45 seconds of teleoff, all teams in the match receive a cooperation point, which will influence the team's rank in the tournament. The number of played notes needed for a bonus ranking point is also reduced. Robots are protected from contact by their opponents when at their podium, off the ground, and during the last 20 seconds of the match while in contact with their stage. As time runs out, robots race to get on stage and deliver notes through the flat and into the track. Bonus points are awarded for harmony when robots on stage use the same chain. On-stage robots earn even more points if a human player spotlights the robots on a chain by scoring a note on the chain's corresponding microphone. The alliance that earns the most points wins the match.
All right, so that is the game that this robot was built for.
They certainly give a lot of different combinations of scoring opportunities. And so make a robot that does everything is intentionally very difficult. And so that's where within our resources, we have to decide, not only how to do those individual tasks, but which things we do and don't do.
Which
In
to
this-
prioritize.
Yes, and in this particular case, we were actually very successful and were able to do pretty much all the tasks and do them pretty well.
All right, so this is the CAD drawing of the entire field. So you can see it's 54 feet long. It's got these large aluminum truss structures in the middle, and you can barely see the chains hanging. So this is what these 120-pound robots hoist themselves up onto these chains at the end of the game, up off the ground. So at our practice area at those Pueblos, we built replicas of these different field elements out of plywood. So here's what it looks like in the classroom next to the wood shop on any given practice night. We've got the robot in the middle. This is what we call the speaker that's got the slot that it tries to shoot into, and then this is a piece of that, truss structure that would have the chain on it. And then over here at the side is what's called the amp that the robot tries to put the notes down into. So anybody have anything to add here?
Well, you see Alex is in the back there. So he's often fixing the code and
We
that's.
moved the desks out of a classroom and moved that stuff in every night and then practice. And then move it all back out and put the desks back in the same place.
And I would just say it's like I said, obviously that angled opening, the speaker is, as with all these games, the closer you are or actually touching the bumper on the bottom, you can have a robot that just is not adjustable. You can bump up against the bumper and shoot your game piece in. So very, very basic robots can contribute to the alliance. The amp on the other side, and we saw that on the video, is more like a mail slot. And so it's a completely different orientation as to how to score. And so in this particular case, I don't know if anyone really made any mechanisms that could do both. So you kind of had to have two different, it's a different delivery metric. And so, we spent quite a bit of time trying to figure out how to, direct, do one task or another task, with a common loading on the robot. Fire, there you go.
All right, strategy.
Okay. Well, elements of, okay, so this is strategy about understanding the speed, maneuvering, how to use machine vision, auto line, slightly with software, I don't know.
Yeah, but I mean, so these are the parts of our robot that help us score lots of points, right?
Yes, because we need to make sure that it's aligned properly, it has good enough speed. Our robot's very durable. So let's say if a robot knocks into us, we're not going to easily fall over, which does often happen. We also have a pretty good spare shot and we're really good at any game. As you see, this is pretty hard. A lot of people are not able to do it, a lot of teams. And that's what one of the things we're known for, which is our trap shot.
So one example of the strategy is one of our competitions, the driver was having a little bit of trouble aligning to the amp because visibility was a bit poor. So we got the position of the robot on the field from the tags that were mentioned previously, and then the robot kind of snaps to the desired position. So the driver just has to get close, and then the robot does the rest, sort of that sort of thing.
Were you planning on showing a video of a match?
I wasn't planning to. I've got our reveal video here, and I've got our video from Champs.
Champ's video would be.
Well, okay. Yeah, all right. I think
kind
it's
of-
also important to know that, like, you go to a regional. Sarah, you want to, what happens at a regional? How many teams are involved? Like, give the background there, because most people don't know anything about it, right?
Okay, so when we go to a competition, when we go to a regional, often there's like, I don't know how many teams, there's probably like over 50 teams.
50 high school.
Yeah, 50 high school. They're all high school teams. Or 50 high school teams. We're all competing. We normally have first day practice matches. So we're just all request to have a match to join and practice stuff. So that's often people aren't practicing. They're not really using their best of the best techniques. And then we have the second day, which is qualification matches, which is where we are randomly assigned alliance teams. And then we have to compete and with these teams and cooperate with each other because we don't get to choose during these days, but we still want to earn points. So sometimes we're with the best team. Sometimes we're matched up with the worst team. We have to think about how can we work with this team to still win our matches. And sometimes it's us working together to fix someone else's robot or just deciding the best course of action and how to play during the match.
Yeah.
And after that, there's
I was just gonna say, the typical match is 2.5 minutes long.
Yes.
And it's basically, you saw with the game there, it's basically 3 robots versus 3 robots. So every qualification match we play, we have 2 other robots in our alliance against 3 other robots, and like I said, they're pseudo randomly assigned. So the figuring out what everyone's strengths and weaknesses are within your team or the other team and figuring out how to play that that match, that gameplay strategy play match by match is a big part of this competition. So it's like if you went and played basketball and you literally played with a different team every, every 10 minutes, it'd be hard to figure out how to play. So that's where we put a lot of our effort into understanding, and we'll talk about scouting and such. So,
Analyze. So we have to analyze data and we have to collect our own data. So there is some like 2 websites where we can get some data on the other teams, but mostly we have to collect our own data during competition, which we call it scouting. And this is done by all the team members where we're watching the matches, saying who shot this, how many points did everyone earn, our opinions on the robots, and we need to collect all this data. So we're pretty good. A skill that we practice is collecting data, like live data from watching the matches, which then the strategy team, which is me and a couple other people, we analyze this data, look at generate graphs. So we have our own
Yes.
website. You want to talk about that?
So we custom make our scouting software each year. For the past couple of years, it's been custom made for each game. And that data then gets all saved, and then we can calculate specific metrics. So we can weight all of the parameters individually. So for instance, how many notes they got into the speaker, how many notes they shot into the amp. We can weight all of those metrics to different amounts depending on what we want to look for in a teammate.
This also generates a graph, so we can actually see their progress over time through all the qualification matches, which is very helpful because we can say, hey, they're on an incline during the whole time, but then they maybe had a drop at the end, maybe they broke. There's always stuff that can happen in between, and the graphs help to show if are they overall improving, have they stayed the same, or have they been decreasing in ability over time. So that's very helpful, which then comes up to the 3rd day, which is finals, which is where we have to choose our alliance. So qualification is where we don't get to choose, but then finals is where we get to choose who do we want to team up with. And normally it's the top.
So the top 8 teams from qualifications, they are declared alliance captains. And then it basically goes down and back up for the teammate pick for who you want to select as your teammate. So if you're an alliance captain, you're going to be wanting to select your teammate. We've been in that position a couple of times. Or if you're a first pick, then you will help your alliance mate choose their second pick.
That's why data is very helpful, because if we are an alliance captain, we got to know who do we think will be best matched with our autos, with our play style, who's going to work well with us, and who's also a really good team. And we always have to choose 2 people. So the first pick's pretty easy. Second picks is normally the harder one to choose, mainly because we need to know who's kind of like a diamond in the rough, or who's good to support us. Because by the 3rd pick, often a lot of all the good teams are taken. So you need to know who has good skills that matches with our, even though it's not top 8.
Let me recast that my way, like to make it like more digestible, I think so at the beginning of the season, you get a 106-page PDF document that are your requirements. They outline the game. We compete on the world stage. So we've competed against teams we've competed, let me be on camera. We've competed against Turkish teams from Israel, teams from China. They all come to our competitions. In Houston, if you're lucky enough to qualify, you have to win a regional. We compete against 625 other high schools. And they've all built this. And I never had this opportunity in high school. This is an amazing program. My son showed up one day and said, hey, I signed up for a robot team. I just about jumped out of the chair. Right? And then we were having trouble. He was having trouble kind of wanting to go back, and I was dragging him by his collar. He couldn't hold a drill. He couldn't do anything. He left knowing how to completely CAD this robot from the ground up. And the students do it all. They machine it, they CAD it, every hole, everything, right, is on here. Mentors, they do have to reach in because they love to touch stuff too, but they're not really supposed to. And we make the students do as much of it as we possibly can. They really do achieve it all. And it's completely programmed. Autonomously, what this program actually teaches you is how to run a small business, right? Because we have to fundraise. The business side, they ask for money. We have to allocate a budget. We do all of that. This robot costs about what? 8,000?
$8,000 to $10,000, yeah.
Each little motor on here. How many motors are there?
15.
15 motors, $200 each. The controllers that drive them, they're another $100 each roughly, right? So it's not cheap. The batteries alone are $100 a battery. We have to have 8 batteries because we go through them very fast. The match is 2 minutes and 30 seconds. So in the end, when these kids enter college, they have an understanding of how to manage a team, how to deal with design requirements, how to use source control in software, how to deal with an assembly. If any of you are CAD people and you've assembled something, a giant thing in CAD, and this part has to fit with this part, we have all kinds of problems fitting parts together, and we have bad behaviors from students who don't properly manage their parts, and we have to figure it all out in the assembly. All of that is an incredible learning experience that these students get. And when they move to high school, they know more about CAD than most of the engineering students do, because they actually have to produce something in 6 weeks. And it forces you to learn, and it's hands-on 100%. And if you don't do it, you face the agony of defeat. And it is brutal to watch. And by the way, these robots, they break all the time. Now, our robot's perfect. It never breaks. How many times did it break?
0.
Yeah, 10 or 15 times. You learn about the you have to design stuff into it, and it evolves, right? This robot is the same robot that we started the season with. We were constantly adding features and whatnot.
Yeah, so we're constantly making iteration and modification to our robot to improve it. So it's helped us to think, instead of just being in a set mindset, like, oh, this is how our robot is, we have to think, how can we improve it and make it better so that we can compete better? Because that's what we want.
And the hardware side of the house and the software side of the house often don't get along.
That's not right.
So they're experiencing that, right?
Really?
And so, yeah, and the way Alex wrote it is not the way the driver drives it. So the driver's at fault. Well, the driver's mad at the programmer. And then the hardware is supposed to perform a certain way, and software is upset at the way the hardware was designed, right? This is going on in high school, and I want to win. And they all are driven by that, not my desire, their own desire. Some of these students, not all of them, some of these students haven't ever been on a team and in competition, and it wakes up some fiery blood in them that they get super excited about. Yeah, so that's kind of the background. And when you look at Houston and you look at what the values that this program brings to high school, it's an amazing thing. You have to build something from scratch. From that silly little video you saw with the underwater stuff doesn't mean anything, right? You get that next video that shows the game, and you're super excited, and that's like January 7th, right? And then in 6 weeks, you have to have this ready to go. And it is a struggle. And we meet every night after school, every night. So you got to do your homework. There's actually t-shirts that say, I didn't do my homework of robotics. And then we have to kind of like, no, that's not good to project that, but it's that intense, right? So they do an amazing job.
Amazing opportunity.
We show the champs video.
Sure.
Yeah.
Made by a student.
This is the year before last, so it's a bit again. Cute game. Oh, that's like. That's bad. That's the
All right, obviously a different game. That was 2 years ago. So picking up those blue, purple inflatable cubes and then the yellow traffic cones, which you don't think about it, but when your robot has to pick up a traffic cone and it might be tipped over and you might be looking at it this way, it was a big challenge. But going to the championships was a remarkable experience, I think, for everybody that went. So. Let's see. You want to talk about the different teams within the Octobots?
Yeah. So, as has been said before, we're pretty much entirely student-led, which is really cool. We have a bunch of sub-teams that handle various aspects of getting this robot to creation. We have business and fundraising, who basically fundraise, as has been said before. Strategy, who does all of the who helps with designing the bot and then supplies strategy at actual competitions to help us score more points. CAD and fabrication puts the robot together, designs the robot from the designs of strategy.
And 3D model it.
Yep, 3D model it, everything, puts it together. Code and software programs the bot in all its entirety, including all of the translation between driver inputs and the robot's control, including autonomous. And then we have logistics, which is supported through
I'd say parents and our team captain.
Yes.
I'd say mix of both of them and the
Yeah.
mentors.
So we're very lucky to have a bunch of supportive parents who help with us with getting some of the logistics sorted. And yeah, we have a leadership committee for parents to list this.
Right. And so anybody's welcome to come check us out online or in person. I've got the link here and the QR code to the website. There's an off-season competition coming up in Ventura at the Ventura County Fairgrounds, October 19th and 20th. So if anybody wants to come down to Ventura and see what a competition is like, it's off-season. It's not quite as high pressure, but you will get to see the full-size field. You'll get to see, robot alliances competing, playing this game with the orange foam rings, the notes. And then we practice during the off season on Monday nights from 6 to 9 p.m. in the Dos Pueblos wood shop. And then in January, once we know what the new game is going to be, It's most nights of the week and usually a weekend day at least. Because it's
Typically Monday, Wednesday and Friday and Saturday. And if everyone feels more motivated to do more days, sometimes we meet up a little extra just because we really want to put effort and we really want to do well. So that's the students making more time and then graciously asking the mentors to show up during those days.
that's January, February, March. Is that? So that's the end of the slide presentation. Are there any questions? And then we can fire up the robot and show you what some of these maneuvers look like that you saw in the video. Yeah.
You said you have a bunch of people on the coding team. How do you, even in industry, that's sometimes a challenge. How do you delegate or divide up the work?
So it's pretty challenging. So right now we lost seniors last year and we have a bunch of new freshmen. So we're walking them through a training program right now to get them up to speed on how to program the bot. When it gets to actual season, typically what we'll do is we'll divide up into groups of like 2 to 3 people, and they'll work on a single subsystem of the robot. So maybe they'd work on the intake or work on the shooter, and maybe there'd be another team for like commands or like controlling the robot from the driver's joysticks. So we just basically divide up into teams of 2 or 3 and work on distinct aspects.
There are merge problems
Sure.
that happen, right? And so just like in real life, and the teams have to deal with that. And it's incredible what it teaches you, right? It's like a real world experience. I've managed software teams before, and it's like same problems, right?
In fact, I was just gonna say one thing. Obviously, we do tons of tuning and fine tuning. We try to automate and combine functions to make, by making the driver's life easier, we make the robot faster and therefore we make more points. So, certainly we combine a lot of functions, automatic sensing, signaling. We got LEDs, flash different colors, telling the team what's going on. Probably one of the big things that we haven't talked about in great depth. We've talked about this autonomous portion of the match, right? The first 15 seconds of the match, where the robot's completely autonomous. We don't have room to do it today, but you saw on the field that there were rings on the ground. They're laid out in a specific pattern. We are capable in 15 seconds of 5.
Yes.
Yeah, and with a bunch of different configurations, we have some rings that are ours from our alliance, but there's also ones that are in the middle of the field. And so there's actually situations where maybe a robot from the other team is actually faster and goes and picks up and steals a note. And so we actually have different combinations and the ability to detect and change paths. But to watch this thing fly around and pick up and shoot 5 notes to make all those points in 15 seconds is pretty amazing. We put a lot of work into that because basically in that autonomous portion, things are generally worth double. So you could actually, a really high performing team can actually get far enough out ahead in the first 15 seconds of the match that all they have to do is maintain their lead for the next 2 minutes.
We have a total of 5 cameras on the bot. 4 of them are detecting these tags, which I went over briefly before. There are 2 on the speaker, which is the target you have to shoot into, 1 on the amp, and then a bunch around the field. 4 of those cameras are connected to 2 orange pies, which basically do some complex math to figure out our position on the field from these tags. And then we have a 5th camera that we use for actually using machine learning to detect these, so the robot can rotate towards them, which makes it much easier for the driver to pick up the notes.
The cameras are set at angles.
Yes, the cameras are set at angles to cover the widest view possible with like as little overlap as possible. So we can basically see tags all the way to like out here on both sides of the bot.
You have libraries of functions for motor control and.
Oh, yes, absolutely. There's a lot of standard libraries I think that everyone kind of builds from, but like I said, there's a lot of glue between the stock libraries too for getting the functions we want.
The documentation is also lacking a lot of the time.
Yeah. Is your firmware up to date? Do you have the right version of the code? Yeah. So a lot of questions we ask all the time. Good.
So if people on the Zoom want to ask questions, feel free to unmute yourselves and ask questions or raise the Zoom hand or type in the chat, whichever you feel like. I noticed the game didn't have too much interaction between the two sides of the field for some years. There's a lot more.
Yeah, so this is
Is
the
that
field.
different?
You have to collect the notes on one side of the field and then traverse back to the other side. So there is interaction between the robots as in,
So there's a lot of high-speed head-on collisions. So there's standard bumper, like some parts, a lot of parts of the design of the robot, in addition to maximum weight and size dimensions and how far we're allowed to extend, because it's not infinite. The design of the bumper material is very standardized because there are very high-speed collisions and we don't want to be doing that.
Step box.
robotics.io.
It's developing, the program is developing an alumni participation, right? A lot of students who leave, you can't get this competition anywhere. And during your high school years, it builds a bond. And so we have a giant Slack resource of all the former students, right? That go, and then some people in the world, they do things like this. They create essentially like a chess ranking system for the performance of the teams. Why don't you put where we ended up this year? Because it was a pretty great achievement.
Oh, yeah.
California.
Actually, here we just,
Just scroll down, will be like, you went, shouldn't have to go.
for example,
Change your votes per page to like
just go
100.
to California.
But it's an incredible program. So a former alumni put this website together that collects data from all of the teams globally, right, from all of their competitions, and puts them on this website so you can sort of search and ranks them in terms of their each part of the game, like earned points in the autonomous period, points at the end of the match, creates a series of metrics. And by the way, I wanted to land this plane earlier. My son was also introduced to data analysis because of this program. Because what happens is we scout, we talked about that earlier. We collect data like this, like put it all into a spreadsheet, right? And then meet at the end of the competition, the round robin competition is the first part, right? We have and then you have to decide who you want on your team. And we have to kind of break down what makes another team good and how will it fit together. So it teaches students how to build a team, which is a subtle thing that is surprisingly important, right? Are they going to be a good fit? Do they drive with us? Do they have a robot that's reliable, right? We kind of alluded to it. A robot that's getting better over the competition statistically is better to have on your team than a robot that is going down over the
They
competition.
might be lower ranked, but their performance over the last, 3 or 4 matches might be greatly improved. Maybe they figured out something that, they were fine tuning. And so those are the ones that if other people don't look at that data and notice it, like I said, there's a diamond in the rough, secret weapon.
So my son learned Excel macros to better process the data because of this program.
I do have a working version of the website if you want that.
Whatever you guys want to show. But like, where are we ranked? I was trying to land that plane.
133rd in the world according to this team's rank, and
10th in California.
10th in California by this rank.
370.
282.
282. You got California there. So, okay. So the ones that actually got there. So 10th out of 282 teams in California. So not top 30%.
Yeah.
Yeah.
So second year, we're number 10. Yes.
Pretty damn good.
Yeah,
It's an amazing experience.
it is.
Yeah.
I guess we want to move to
Ready to play?
Let's not run into anything. Let's give it a drive.
Might get a note to catch.
let's take a minute.
You guys look at
It's gonna get loud.
Yeah.
Get loud.
Do I have to duck under the desk?
Maybe.
No need to.
They do try to make it so that anything that's being thrown from great distances
Yeah.
is soft.
Does it stop sharing the screen?
What about?
Let's share.
So
Oh, but I share my screen.
Richard, do you want to talk a couple notes on the map? Thank you.
I'll get that fired up. What's amazing is the drivetrain for these robots have really moved from sort of tank drive, 3 wheels and arcade steering to a full what we call swerve drive. So each, there's Omni drive modules on each corner. So
These are here actually.
yeah, so the orientation and direction we're driving are all independent from each other. So we actually take great advantage of that in the autonomous. You know, we can drive downfield and have the gyro actually click us to the orientation before we, you know, when we shoot things. So we can actually be aligning while we're driving.
So this is the drive motor and this is the steering.
So,
Has a-
but
for steering.
give it to them.
Yeah, cool.
Yeah, give it to
All right. I like it.
them. So
This is a camera? or which-
No, it's just a motor.
it's just
Oh,
the
that's the
steering
motor,
stack.
this
Yeah,
is the motor too.
Yes, so this is our drive motor and this is our steering.
Oh, this is, oh, yeah, I see.
so the planetary gears, planetary gear set to gear it down to like. Yeah.
Just be able to do.
Yeah.
You should be able
It's only
to.
by
Can
students,
you
yeah.
reuse parts like that? in the
Yeah,
next robot?
Yeah, this is,
Oh, gosh, there.
we typically have radio, this is auto design, so we like. Yeah, we have customers for, like, a lot of teams just buy it off.
I get an hour budget for your batteries. Yeah.
So
we can go
designed
to
our own.
25.
We didn't have the budget. to buy a rubber. So we
And then.
designed our own wheel, this is good and not better.
Yeah, it'll be, the breaker, the soft breaker, 40 amps.
Each wheel per minute faster than this breaker, so I think.
So if you guys want to look to the front, here's a video that I took personally of us trapping on a practice structure. So this is how we would trap.
Yeah,
Oh, my bad.
the challenge here with the end game is so climbing on a chain might seem fairly straightforward. Except that the real task was that there was this window to place the node in, you know, an additional 2.5 feet up in the air. And of course, the game design committee figured out that the limit for how much we could extend is kind of underneath that. So you had to come up with a really crafty geometry in order to be able to climb up and do this placement. In fact, the chain, if you come up and look at the robot later on, the chain is actually, you know, when we climb up, right, we pull the chain down and the chain actually kind of lives in a little slot down the middle of the robot so we can stay balanced and level.
Yeah.
You know, other people made designs where their robot climbed and then tilted over and landed against the wall. So when our first competition we went to this last season, you know, out of 50 robots, there was only 3 that could do this task at the beginning of the regional competition season. By the time we got to the last week, you know, there was probably 25%, you know, so it was sort of a hard bonus task. And I'm really proud of how the students managed to, you know, make a functional design.
Is that chain put there for that purpose, or is it just a security chain that you?
Yeah, it's for the purpose. So for that purpose, so it's on all the structures. So if you look here, they have every single angle of the stage has a chain. So everyone's supposed to be able to do it. Not everyone's able to do it.
Yeah, but there's one other design thing that I'd like to point out, which is that we're reaching up to put these notes into the slot, reaching up to climb the chain. But one of the things we decided early on was that with 6 robots racing around 25 miles an hour on this field, that we needed to be able to go underneath the chains to avoid collisions and get from, you know, the place where we score down to the place where we pick up our next note, because that's the game. It's 6 robots running back and forth. So everything has to be below the height of that chain. So whenever we need to reach up, then things have to, you'll see this thing pivots up, these arms extend up to climb the chain. So we stay below the height of that chain and we can go under these structures.
Here, watch out.
So there's the climbing arms.
Can you stop the share?
Oh, sorry. Yeah. So there's the climbing arms extended.
You can roll a note in.
If you're ready, you kick it in. You know the gyro. That's what we do for shooting into that mail slot thing is.
The amp.
Yeah.
Here, stand like this. Show us everything.
Here, how about we place it this, so you can see it going, yeah. That's Can you just tap Wi-Fi? I just want to see what it does. Yeah, just tap that.
Those lights are similar to you or just for decoration.
Or what?
The different colored lights. do they
Okay,
do something?
so those are to tell the drivers what the bot's doing, what it's thinking. Because when it's across on the
Right.
54 feet away,
Yeah,
it's really hard to tell if it's picked it up. Like even if it's just like on the other side of the stage, the big truss structure, it's really hard to see if it's picked it up. So having, big glowing lights blinking out code saying, green, like purple, okay, it's up in the
yeah, so that gives you your
it's up-
status.
yeah, it's up in the bot, but it's not ready to
I saw that.
Yeah.
I saw that.
Piece of
Make it
protection.
so they're not gonna crash it.
So it doesn't, so it doesn't communicate back to you, you talk to it, and talk, I mean, other than that.
No, it like outside of the piece detection, which kind of like has a bit of autopilot to it. Other than that, it doesn't like tell us anything outside the raw
So it
telemetry.
does automatically, it sees it
Yeah.
and can help find it.
Yeah,
itself.
we actually just got that working on Sunday.
Yeah.
That was like other big
Kinda cool, right?
Oh, yeah, I was wondering if you were doing that.
Nobody's driving it.
Yeah.
It centers itself up automatically.
It's exactly, Amazon's probably spent zillions of dollars building these kinds of things for their warehouses,
They have zillions.
What?
They have zillions. Yeah, gave about $10,000. It's about a basketball court in size.
Yeah.
Yeah.
The lights are
So
indicate when a node is picked up because it's hard to see across.
Yeah, yeah, of course, yeah.
okay, Zoe. Yeah. So you're talking about facing this way, Daniel? Okay. Yeah. And then let's just do a shot with nothing. Like nothing.
You catch it.
Pretty fun, right? And we're shooting into a slot that's what, maybe like 6 or 8 inches high. It's about 6 feet off the ground. And we're shooting it from,
that camera is.
yeah, and we're shooting from 20, 30 feet away.
Does the machine find the spot and
The machine finds the tags, finds those, and then we,
finds the tag.
those are called April tags. Yeah, they're kind of like chunky QR codes, and there's a bunch of them placed in fixed spots around the field. So with all the cameras on the robot, it pretty much knows where it is on the field at any given time, because it can see, and it sees that one this far away, and I'm seeing it at this angle. Therefore, I must be here, and I see this other one over there, and it can triangulate.
And what is the quality of the, like, take that multiple camera, take multiple tags?
So
It actually. Brings away that, let's get it, let's get it. Break anything. We can't afford it.
Give you all your toes. Let's do some more.
Yeah.
What's the weight of those discs?
Like this?
Those one, please.
Yeah, that's one of them. I can tell you exactly.
There's some.
Not very much.
That's a well-used one.
Yeah.
They used to have all skin on them.
There's a cleaner one.
They do a good job of like making it so high school students can't kill themselves with, things. 'Cause Michael's been hit in the head several times before.
Oh, yeah, I've also been hit in the head a couple of times, not necessarily by the robot.
Want me to take that from you?
Screen here. Now that I know where.
Oh, wow. Why? Yeah, why did that?
We don't need to drive anymore. Let's get some questions.
The ankle tag is still
I'm gonna
up
turn it
there.
off if we can't. What's that?
You pushed by? Fire. I hit amp prep and then I hit fire.
Take it down.
I hit amp
It's
prep,
probably scanning it. That's probably what happened.
fire it back down.
What happened there was it scanned, it probably scanned it and then tried to do it.
Yeah, I probably thought that was it.
It was a software bug. We have them.
I have so many of them, in fact.
Those aren't real. What are you talking about?
Yeah, we
So
can look at all kinds of sensors, infrared sensors, magnetic encoders, laser sensors.
Can you see the robot? Can you drive? Actually, can you drive the robot out here? So if we didn't make it clear before, this is the camera that detects that QR code. That they program, they do the trig and whatnot, and they have to actually calculate the.
There's a library that does most of the math for us, but we do have to do some fusion between that, and we also have odometry on the encoders on the drive motors too. So we do have to do that fusion.
The PID control is the students are introduced to PID control, and they're actually also introduced to state space control, which is kind of a more like a next level, but you don't really need it, thankfully, because state space doesn't really add a lot of additional value. But there's a lot of things that these students are introduced to as part of this program that I didn't really ever understand and appreciate, and they keep current. The April tags are now in the library sets that you can use, and it gives you back an XY coordinate, and then you kind of have to put together where you want to aim and shoot. And the students do all that work, right? And what's great about it is they want to do the work because they want to win. I don't have to really push too hard on that. Just have to keep the head focused in the right direction.
And on the mechanical side too, there's design of the motors. Each of these motors has a stack of planetary gears. So you have a motor that's designed to run at a certain RPM and with a certain torque, but you need different amounts of torque, power, speed for each of the different robots. Like the robot that hauls this, the motors that haul this up on the chain need different gearing than the motors that drive or that turn the drive wheels. So that's all, has to get thought through so that, do you want the robot to be, particularly fast, or, you need the robot to, hold its position and have a lot of torque so that it can push another robot out of the way. So all these design decisions are.
Yeah, and we do,
early on.
currently we do power management, because again, there's like one motorcycle battery. And there's a 120 amp breaker. So that's all the teams use the exact size, exact same battery, exact same breaker. A lot of the control system components are the same. And so we actually learn how to manage, and not brown out the system, because that's,
Yeah, how do you keep the robots from being hyper dangerous? Right? You give them a robot, a motorcycle battery that can only give off so much power over time. And so we've learned, and we're constantly struggling on how to get the most out of the battery in 2 minutes and 30 seconds, right? And if the power drops below 8 volts, right, it'll reboot, right? So we can't do that. And so when you have 15 motors running, Michael, what are they, horsepower? What are they?
yeah.
700 watts?
Well, some of them, you're generally about 300 watts is about the most output from any one motor at 12 volts or 10 volts. So it's, like the four motors at the corners accelerating it, so it's like we put an 80 amp limit on all 4 corners. I mean, instantaneously as we accelerate, there's 320 amps. The main breaker can stand a little bit of, and we actually characterize very carefully. It's like, because it's just a thermal switch. But if our battery has a certain internal resistance and we don't ramp the acceleration rate, the voltage of the system may drop. So it's And we learn those by failures a lot. It's like, oh, it's not working right. Well, what's going on? And then we go debug and we look at charts and we, and do a lot of root cause analysis. So it's a whole bunch of real world learning.
They understand what gear pitch circles are, right? They,
A lot of applied physics.
they have to figure out how an elevator works. They understand what bearings are, like in practical sense, right? They, we learn that we need to standardize on parts to minimize like a whole bunch of different parts because they break all the time. Yeah, but students, you should really be doing the talking instead of sitting. They're hungry. What have you learned?
Question back here.
Yeah, please.
Is there a weight range of the system?
So by definition, the robot itself, without the bumpers on it, without the battery, is 125 pounds maximum. So really on the field, it's pretty close to 145, 150 pounds maximum. Lots of teams that want to do everything, fight that weight limit and learn how you have to go light and stuff. It's like, suddenly everything's heavy. There are teams that make much smaller robots, and like there are some little dinky ones that are 70, 80 pounds. And so again, less mass, better acceleration, faster, more maneuverable, but it's a lot harder to make all those functions work in the smaller package.
You still have the small ones competing with the big ones?
Oh yeah, it's all in the same field, absolutely. So avoid getting hit instead of being able to hit hard. And there is a lot of defense being played. You're blocking. It's just like basketball. It's like, to let my other high scoring guy do his thing. I block the other ones, and there's 5-second pin rules. There's a ton of rules and a ton of zones and stuff. So it's
I used to describe it as you're trying to make a robot that's able to replace a basketball player. It's like you're making a robot play basketball and you need to win the basketball.
Have you tried any AI on these agents?
So yes, we are running a YOLO model from this camera for the note detection that I did before. So it turns towards the note. We didn't actually do the implementation, but it but it's built into the library. But we took the data from there and we put it in the new position.
YOLO is.
Actually, it's not YOLO. It might be. I forget what the name of the exact model, but it's an AI.
Other years, like some game pieces, a couple of years ago, were these giant tennis balls, and there was red ones and blue ones. And if you're the blue alliance, you could make points with the blue ones, and if you scored red ones, you scored points for the other alliance. And so we actually had machine learning. We were trying to teach the camera to detect round balls on the field, and especially since half the teams, basically the alliance colors, we changed the bumpers every map. We're on the red side of the field, we have red bumpers. Other side of the blue bumpers. The game design committee very intentionally did that so that you've got all these robots running around with their bumpers, but you're looking for round balls. And so a lot of work on trying to figure out how to get to the balls we wanted. So with various success. Yeah.
Are the batteries standardized? That seems like an area where you could cheat.
Nope, very standardized.
Very standardized.
Sealed lead acid,
What are
17 amp hour.
Yeah. Okay.
Yeah. We
That
use
looks like
them
it's
at probably, we probably,
punctured.
we probably use them at not 10 times, but 5 or 8 times sort of the standard consumption. Like I said, we probably average 80 amps over 2.5 minutes. So literally it has to get switched out. I mean, already the voltage has been dropping off there. So we have a whole flotilla of batteries. We test them internal, best case, best wiring practices, the largest cables we can use, et cetera, et cetera, et cetera. So yeah.
Color coded by what year we started with them. So there's a bunch that are yellow.
They only last,
labels, red labels.
they only last 200 or 300 cycles, and then we recycle them and get more. So.
Everybody gets the same battery? Yeah. Is that the?
Yeah, we get a limited number of components, with our very expensive registration, we get a kit of parts, and it gets a battery and but we have to go buy our own. But yeah, there's literally a list of like, hey, one of these 8 models of battery from these, Panasonic or, MK battery. That's it. Very short list of allowable batteries, allowable motors. On all the non-control side of things, you're wide open. You can use whatever cameras or co-processors or whatever you want. So, but yeah,
About that battery question, amusing anecdote around data analysis, right? So one year, we asked each of the teams, the 50 other high schools that are there, we scout. We asked like, what's your robot good at? We put this all in this spreadsheet to assess what team's a good team. We asked a weird question. We said, how many batteries does your team have at the competition, right?
and at the end,
And it matched, it correlated 1-to-1. The most batteries was the top performing robot.
Wow.
The resolution of the number of batteries you have is not enough to determine the bank.
but there's, yeah, so.
But so you have like teams that, and basically it's also a kind of correlates to budget, right? So if you can afford a lot of batteries, because they're $100 each roughly, right? You can compete better because you can practice more. Some teams would show up with only 4 batteries, and it speaks to how much resources they have. And that's actually a detractor in selecting them for your team. But that's going on at the high school level, right? With this program, which is, very useful for later life.
You can learn more doing this than reading 100 textbooks.
Great, thank you.
All right.
Thanks, and thanks to the people on the Zoom. And we'll be back with our next meeting in October, on October 9th. Thanks.
Thank you.
Thank you, everyone.
All right. Missile in the next